Next, let's do one example. Here we have a piston cylinder assembly, and what's inside is water. And then you see this short dashed line around the boundary. That means the system is insulated, so there's no heat transfer. What we know is this is a compression process. It starts at G point, meaning the beginning is saturated water vapor, and the initial pressure is P1. And then at the end, the pressure is P2. So P2 must be higher than P1 because this is a compression process. What we want is to sketch this process on a T versus S diagram. First case, when the process is reversible, and second case, when the process is irreversible. Okay, so now let's start from the diagram, T versus S diagram, lowercase s. First thing first, the vapor dome. And on this vapor dome, we have two constant pressure lines. Curve up, straight, and curve up. Curve up, straight, and then curve up again. Okay, so which one should represent P1 and which one should represent P2? We know P2 must be higher. The final pressure must be higher because this is a compression process. So P2 must be on top. The higher you go, the higher the pressure it represents. The lower one should be P1. Okay, all right, and let's draw this line longer. Okay, P2. This is my P2 line. Okay, so now we are going to locate point number 1. Where's point number 1? We know point 1 must be on P1 line because the pressure of point 1 is P1. And next, we know it's G point. So point 1 is really easy. Point 1 must be here. Point 1 must be here. Okay, next one, we need to locate point 2. Point 2 must be on P2 line, but where on P2 line? So we have a few options, right? Point 2 can be directly above number 1, or to the right a little bit, or to the left a little bit, or further to the left. So we don't know. Let's do case number 1. Case number 1 is reversible. What we will start with is the entropy balance equation. Delta S equal to integral 1 to 2 delta Q over T integration over the whole boundary plus sigma. Okay, so now case number 1 is reversible. What's going to happen? If the process is reversible, sigma must be 0. Second term in the right hand side goes to 0. And next, remember the short lines around the boundary. That means the system is insulated. There's no heat transfer. If there's no heat transfer, Q is equal to 0. If Q is equal to 0, first term goes to 0. There's no heat transfer. Adiabatic. So what we can have is the whole thing is just equal to 0. Delta capital S is equal to 0. So what is delta lowercase s then? Delta lowercase is equal to delta capital S over m. That's the definition. So that's 0 over m, which is 0. And s, lowercase s, is my x coordinate. So for case number 1, 1 to 2 must be a vertical line. Why? Because your x coordinate doesn't change. Delta s is equal to 0, and s is my x coordinate. If it doesn't change, it must be a vertical line. So 1 to 2 must be a vertical line, and number 2 must be on P2 line. So 1 to 2 goes straight up. Goes straight up. And that's where number 2 is for case number 1 if the process is reversible. Okay, so our conclusion is 1 to 2 must be vertical. for case number 1. Now we move on to case number 2. Case number 2 is to say the system is not reversible anymore. It is irreversible. So what is going to happen? We start from the same equation, delta capital S equal to integral 1 to 2 delta Q over T over the boundary plus sigma. First of all, it is still adiabatic. There's still no heat transfer because the short lines around the boundary still exist. That means the system is still insulated. No heat transfer. So first term in the right hand side still is equal to 0. And then the second term in the right hand side, what's going to happen? If the process is irreversible, the whole right hand side just becomes sigma. And we know if the process is irreversible, that means sigma must be greater than 0. So delta capital S must be greater than 0. And then what is delta lowercase s? That's delta capital S over mass. And we know delta capital S is just equal to sigma over m. Sigma, we know irreversible must be greater than 0. And then mass always positive. So we can say delta lowercase s must be positive. Delta s must be positive. What does that give you? Lowercase s is still your x-coordinate. So that means your x-coordinate becomes bigger. If your x-coordinate becomes bigger, 1 to 2 must move to the right a little bit. So 1 to 2 to the right, and number 2 must still be on P2 line. So 1 to 2 to the right and on P2 line. So this is case number 2. This time 1 to 2 is slightly curved. Okay, so now to differentiate between the 2 points, we call the first one point 2s and the second one point 2. Okay, so here this becomes 0.2s. What does s mean? S means this is an isentropic process. Do you remember what is the requirement for you to call a process isentropic? First one adiabatic, second one reversible. Do we have those two satisfied for case number 1? Yes. Here, adiabatic, and here, reversible. Them together, that gives you isentropic. And if it is isentropic, delta S must be equal to 0. Entropy does not change. And if entropy doesn't change, that means your x-coordinate, lowercase s, is constant. So it must be a vertical line. So we call this process 1 to 2s. And then we use 1 to 2 as reality, irreversible. 1 to 2 must be to the right because the x-coordinate becomes bigger.